Once you type your password.
Sweet. All right. Good morning, everyone. So today we're going to be talking about cleaning messy data at scale. My name is Dody. Before starting us off, I wanted to thank Verso for hosting the event, and also a special thank you to Kendall for investing so much of his time and energy into organizing such a great event. The data community in Vermont is really lucky to have him. So for today's topic, my goal is to go over 5 different approaches to perform content matching. And I wanted to use this opportunity today to kind of do something that is rarely feasible when working on real-life project, which is having the time to test different solutions, weighting the pros and the cons of each solution, measuring what success looks like so that you can really decide on what's best instead of working against a schedule. So the goal is to share some practical insight from production implementation for that problem. So I currently work as a senior DS at Fairday. It's a local company based in Burlington, and I work on consumer behavior models. So we build models like propensity, recommender, persona for a wide range of customers. I also have a background in NLP. I used to build models to do online content classification. And so for today's topic, our data set is going to be a few millions of raw US addresses that we want to match against a ground truth. We have about 120 million clean addresses that are basically our database. And our goal is that whenever a client comes in and send us some data, we want to append some feature to the data. Things like when was this property last sold, what is the square footage of that property. And so the data can come in pretty raw. It can be from manual form filling, it can be some different format broken in by columns or just a full string. So we have that matching process that has to happen, and the higher the match rate, the better for the data enrichment. I purposely chose that data set to be fairly non-technical because there is plenty to discuss in terms of the technical aspect of those solutions. But everyone has worked with messy text, messy data. Everyone is familiar with some of the challenges of that can be embedded into working with short text, such as US addresses. So speaking of, this is the type of issues that we're going to be dealing with. So on the first example, you have a true match, but different spellings. The word street can be fully spelled with just ST or SD dot. For the second, third, and fourth, we have quite a high match in terms of the subcomponent of the string, but those do not point to the same address. They are different house numbers, different units within the same address, different state. And then for the last one, we have the common typo or fat finger error, but those two addresses are the same. So the idea here is that are we going to be able to find a system to match address 1 and 5 while ensuring that we are not getting any matches for the middle ones? So before diving into the solution, let's just establish some benchmark. So like I said, our ground truth has 120 million addresses that are coming from different vendors. So they have different formats, different level of quality. And our test data is 5 million addresses across 5 different anonymized companies. And I've listed those by their industry. So we've got financial industry, debt consolidation, e-commerce, fitness studios, and home improvement. And you can see just by the raw match rate that we're getting, this is just doing a quick left join from the raw data to our ground truth. We're getting about 47% match rate, so good, not great. This is a starting point. But there is a wide range of match rate that's appearing across those 5 different clients. Financial industry matches at 0 because all the postcodes are missing. And then we have some pretty clean data with the debt consolidation company where the initial match rate is about 80%. So the goal is going to be to implement a set of solution to get all of these match rates as high as we can, considering where we're starting. The 5 solutions that I'm going to present today, they're ranging from basically low level of effort, where the first one is you just throw money at a problem, purchase a contract with a third-party API and see where you land, up until a fully custom NLP pipeline where we will build our own models, make our own predictions, and then compute our own matches. And the idea when we go through these solutions is to understand the trade-off that will lie into each of these and kind of balance for complexity, cost, and accuracy of the match rate. So we'll start with the third-party API. This is usually the first sort of fork in the journey where you have to choose between buy versus build. In this case, we're going with buy. We're basically decided that this is an important problem that we want to solve really quickly. We don't have time or the resources to implement a solution, so let's just pay someone for their experience and knowledge in the products they've developed. So how good can this solution be? This is an example of one of the many services that are available online. I chose to anonymize this because I'm not trying to advertise for any of those. So the way they work is usually just a RESTful API where you pass a curl command with your raw text and then you get a validated address. What's interesting with this one is I purposefully added a typo in the street name, beacon instead of bacon, and the parser was able to correct that typo. However, it didn't perform a full validation because this unit does not exist in that building. There is a suite 201, but there is no suite 201B. So even though the system is already correcting for some of the typo, doing some of the validation and parsing that we're hoping to implement, it's not perfect. However, it is really fast to implement because you're just embed an API call in your system, so you can be basically up and running within a couple of minutes. So now if we perform these calls on our entire data set, we go from a 47% match rate to over 90%. It's a dramatic improvement. We see that we've got much higher match rate across the board. I think some of the interesting findings from this chart are the fact that the system, even though for the financial industry we're not providing any of the postcode, the system was able to get to a match rate of 75%, so correcting for most of that missing and fairly messy data. Same thing, the home improvement. Even though we started with a pretty low match rate, we ended up with one of the highest match rate, so meaning that the data was fairly messy, but rich in the sense that a smart parser could match those addresses to a ground truth. So we're going to call this solution nearly perfect because there's still some edge cases. And these are some of the issues that I run into when doing some of the validation. So often what we see is that the query and the API match are not exactly the same, and they're often closely related in terms of geography. So sometimes we're off by a few blocks, sometimes we're off by a couple of miles, and then for this last one, we were basically looking at a specific unit within a residence of condos, but then the API match gave us the address of the entrance of the condos. So even though we got a great match rate, it's not perfect, but it's going to be sort of our target when we design our own solution. When we think about the pros and cons of this approach, obviously I think there's nothing that you can implement faster than just adding an API call into your system. You don't need any fancy ML infrastructure. You don't need to have your own data. You can just rely on the data that is owned by those companies. You're basically paying for their expertise, and you get a solution that is virtually perfect. However, it comes at a pretty high cost. This is the typical cost for those APIs, so a couple $100 a month for 170,000 monthly call. But if you wanted to parse our raw data, you're talking about 120 million calls. Either you're going to scatter this over several years not to overshoot on your monthly usage, or you're going to pay a hefty price with like an enterprise contract and have to sign on with a couple of years potentially with a vendor. There is no customization that's possible. You're basically getting whatever the API is returning. So it's very black boxy. You're not getting any explanation on why something matches, why something does not match. And like we talked about yesterday, when the topic of vendor versus open source was brought in, you're locked in with a vendor, meaning that you're subject to the price that they want to go with, you're subject to some of the outage, you're subject to their roadmap, and then in addition, you have a contract in place, so you have rate limits in place, and so it's, at the end of the day, it's not a solution that's really optimized for our needs. So let's move into something more in-house. And the idea is, can we build something effective without starting with machine learning? We're going to take the traditional software engineering approach and design a system that is very deterministic, rule-based, of just adding some cleanup, both on the query side and on the ground truth to see if we can improve the match. And we're going to do this in 4 different steps. The first one is taking the raw input and doing very minimal cleanup. So uppercasing everything, removing unnecessary punctuation, helping a little bit with the cleanup of the unit that is fairly free-form. You can sometimes have the pound sign, it can be an apartment, a unit, sometimes it's just a floor, so it would be FL and then floor or FL ground. And then for the next step, we're going to use a parser, an open source parser, to chunk this address into meaningful substrings and isolate things like the house number, the road directions, the postcode, the city, the state, etc., so that we can add final layers of cleanup, but that would be specific to each of these sub-items. And the idea here is that we would, for instance, the capital letter N, we would want to turn it into north if we know that it's in the road direction. But if it's part of the street name, this might not be something we want to correct. So knowing exactly which substring we're dealing with, we can design rules that are specific to each of those and then improve the creation of each of these substrings. And then at the end, we put it all together into a canonical form that would be our cleaned-up version of the address. So obviously this can run fairly quickly. It's just a handful of regex and then a call to the parser. I used, in order to iterate over these rules, I used an LLM. So basically I was doing some cleanup, computing some matches, identifying matches that could not hit, and then asking an LLM to come up with rules to improve the match rate and iterating over this. So I was in charge of the funnel, and then the LLM was in charge of creating and compiling those rules. Because at the end of the day, you can add a ton of rules, and there is a sort of a sweet spot where you're starting to add rules only to correct the outliers, and so your code can get very bloated really fast without necessarily any improvement for the match rate. I want to highlight a few things about the parser. So I was using libpostal, which is a fairly well-known open source project that started, I think, over a decade ago. So it's a model-based parser. So it was trained on a couple 100 million addresses. And the idea for the design of that library was to train a model that was doing address parsing. So every chunk of the address was assigned a label, and that model was trained to predict the label assigned to each of those chunks. It's very fast. The model is very lightweight, so you can run the inference locally on any laptop. As far as the functionalities for this library, I wanted to highlight those two, the parse address and the expand address, because they'll be relevant for us down the line. So the parse address is the main one that we're using for this cleanup. You pass it a string, and then it's going to assign a tag to each of those subset, so house number, roads, unit, city, state, postcode. It's fairly sensitive to the order of your original string. So that's why adding this initial step of pre-cleaning, maybe rejittering a little bit the address, will help with the results of the parsing. And then the other one that is fairly interesting is this expand address. And the idea here is, again, passing a raw string. The output will be a list containing different variation and spellings for the address that you've provided. So you can see that the state, New York, can be spelled NY, New York. The ST for street can also be expanded to Saint. That's one of the common kind of mismatch that we're dealing with when dealing with this contraction. And the idea behind the expand address is to enrich our data with more variation of a given address, so that we can teach the model that one address can take multiple forms, and that the model should learn to handle all of these different ways to spell the one address that we're dealing with. So this is the results that we're dealing with, that we're obtaining after we're doing our whole curation. As a follow-up to one of the talk yesterday, if you don't know about the PEM, which is an open source Python package management, highly recommend it since we've switched to it. We went, I think, from pipenv to PDM. It has been night and day. So if you're looking for something that is very user-friendly, highly recommend PDM. So this is just a simple script that takes in an input string. We'll take the print original, the cleaned up version, and then the canonical form, and then also display the parse component resulting from the parser. So you can see that avenue was cleaned up. The unit 38G was also rejiggered a little bit, and then the city was expanded to a full spelling instead of just an abbreviation. And the idea here is to turn a spelling that is potentially too specific into something more generic, and by applying these generic rules to every single address will increase the likelihood of a hit. So let's look at the results now. So we're going from 47% raw match rate to 76% match rate just by adding a few regex to this problem and the parser. We see that we've got a significant improvement in the match rate for most of those customers, except the financial one. And this is one of the drawbacks of this method, is that it doesn't handle typo or missing information. So we're basically still stuck with our 0 match rate. But overall, making a pretty good progress in the right direction. However, there is this idea of diminishing return. As you add in more and more rules, your code gets slower and slower, and you're basically creating rules that are specific to just a handful of outliers. So it can be, it can turn into an endless quest for perfection. As far as a few errors go, so we have the issue with cities having different spellings. So Alexander City in our original query was known as Alex City in our ground truth. And then we have this issue with addresses belonging to a given postcode, but under a different city. So this is something that we have to fix. So we can see in that second example, the postcode is the same for the match and the query, but the city name was different. And then for the last one is that spelling issue where ST was corrected as street, but then in the clean match, it was actually the word saint. So those are a couple lessons learned that will basically put us on the track of using a model to handle all of these edge cases instead of trying to capture them one by one using dedicated rules. As far as pros and cons for this method, it's very fast to run. You can even on a laptop, you can run over 5,000 cleanup a second. It's very easy to explain because you've designed the rules. You can add some logs to this process to understand how an address is being transformed as it moves through the system. It's very low cost because we're using just open source and widely available packages. You still do not need any machine learning infrastructure. And at the end of the day, you're just dealing with simple string validation. However, like I said, it comes at a cost. You quickly hit a point of diminishing return. You do not, since we're focusing only on the ways things are spelled, we're not focusing on any of the semantic. And that's why this solution is very brittle to typos and spelling variation. And it worsened for complex addresses. So the longer your addresses, the more component they are in your address, the more likely you are to miscorrect something or not correct something, and then fail to have a hit on the address. So the question is, can we do better with machine learning? So we know that the rule base got us to 76% match rate. The API achieved 90%. So where can we land with an ML-based solution in between these two numbers? And the first thing we need to do is to come up with a system that goes from pattern matching to semantic understanding, so that two addresses spelled ever so slightly differently will still be able to match. So the first step we're going to take is using a neural network to encode the semantic meaning of those addresses. And we'll start with an out-of-the-box model. So again, we're ramping up the complexity of these solutions. So we're not designing our own model. We're relying on something that was trained by a third party, and then leverage that training in their model architecture to create those embeddings. So this is the sort of layout of the problem. So we'll start with our two data set, the ground truth and the queries. We'll use the same model to convert every single address into a vector that will encode for the semantic meaning of each of these addresses. And then we'll use vector search to hopefully match addresses that are spelled a little differently yet convey the same meaning. So in the example here, even though street is spelled ST in one case and street in the other one, and the unit is spelled differently and the city is spelled differently, our model will assign a small distance between these two vectors and therefore decide that this match is indeed the right match for this. And so the benefit of this approach, even though a bit more black boxy, is that it has the benefit of handling way more variation without having to craft explicit rules for that matching. So how do we do this? The first step is we need to turn our text into vectors, and we're doing that through a tokenizer. So the way those work is they take raw text as generic as you want, and they chunk the text into tokens. Those tokens are parameters of the model. They were learned during the model training. So for instance, in the example on the screen, the house number, so 61, matches to token 5333, which is matching this vector starting with coordinates 70699 and ending with 65612. The tokenizer is part of the model, so when we're using an out-of-the-box model, we are basically stuck with whatever tokenizer they use for their training, so we cannot create a tokenizer that's specific for address parsing. But we're hopeful that if we work with a model that's generic enough, it will be able to handle addresses because the model will have seen addresses during its training. As far as parameters goes, you have the number of tokens is specified by the user, but the token themselves are learned by the tokenizer when crawling the corpus that you provide as training. And then the length of the vectors, the length of the embedding, is also specified by the user as part of the model architecture. But each coordinate of the vector is slowly tweaked during training and adjusted by the model to minimize whatever loss function or cost function you've assigned. So here's an example of tokenization. This is not the out-of-the-box model. This is the one we'll use down towards the end of the presentation, but I didn't want to duplicate this slide. So I'm showing you how we can go from our original address to the sequence of token, and also leveraging the parsing to help the tokenizer with more context. So we know that with the previous solution, we were able to get a canonical form and also a part version of the address. So we know which chunks of the address are the house number, the street, the state, the postcode, etc. So we can add our own custom tokens around each of these segments to help the model know where it is within the address. So you'll start by saying house and then 77, and so the house number 776 is split into two tokens. And then you end with a \house to say, okay, now you're done with the house number, and then you start with street, and then you tokenize the street. So this will help a little bit adding additional context to the model. So how do we generate those embeddings? For this out-of-the-box model, because we're a GCP shop, I used Google basically embedding model. This is part of their Gemini suite, so it's some of the text embedding that powers their Gemini model. And the nice thing is that they have those models embedded into BigQuery, which is their SQL-like service. So you can create this query that looks like SQL but has a few specific functions like the ml.generate embedding, where you specify which is the model that you want to use for that embedding, and which is the field that you want to embed, and what is the task that you're trying to get that model to perform. In our case, we're looking at semantic similarity. The only thing we know about this model, and this is why it's really just a black box model, is its output dimensionality. So the vectors that this model will produce will be of length 768. The internal specs are not public, so we don't know how many parameters they are. The best guess is that it relies on transformer, which is the main architecture for most of the LLMs today. Once we have the embeddings, we need to perform vector search. So we know we've embedded our 5 million addresses, we've embedded our 120 million ground truth. How do we find the matches now that we've got all these vectors? So the idea here is we would use cosine similarity, so computing the scale dot product between each pairs of vector to find the vector within the ground truth that has the highest match possible with our query. And the idea is, in the example above, two addresses that have a similar spelling but not exact will hit a really high cosine similarity. Perfect match would be a score of 1, no match at all would be a score of 0, and complete opposite semantic meaning would be a score of -1, but that's not really applicable in our scenario. So one of the limitations here is that you can't just be brute force, because we're dealing with 5 million addresses that we have to pair with 120 million addresses. So now you're dealing with 10 to the power of 10 or 12 or something like that, different pairs. So we have to find a way to restrict the pool of candidates each query has to be paired with. And we do that by filtering on some of those mandatory fields. So street number, postcode, and state. Because if two addresses do not share any of these, you know that they're not the same address. So that means that if an address is at 123 Main Street in Vermont and Burlington, we will compare it to all the ground truth addresses that are at 123 house number in the zip code Burlington in the state of Vermont. As far as the results go, so we're now taking a leap forward. We're going to close to 89%. And we see that we were able, just like the API, to correct the zero match rate on the financial industry, and then hit basically being on par with the API. I want to highlight that we're not trying to beat the API. The API is doing a lot more than what we're trying to solve for here. So this is not a solution to replace the API, or this technology still has some value, but we are only trying to find what is the best match possible for a given address based on our ground truth. And like I said, it requires the filters on house number, postcode, and state in order to restrict the pool of candidates so that this can be runnable. But yet it still takes a lot of compute. Embedding the 121 rows took 10 days worth of compute on GCP. When using a highly parallelized compute, we get down to 8 hours, we still burn 10 days worth of compute. So it's a significant improvement, but it still feels a little bit too complicated, and so we're going to see if we can do something better. As far as the errors go, we have the main error now that we're dealing with is the wrong street, because we're forcing the house number, the postcode, and the state to be the same. So the issues that we're dealing with here are all incorrect street. When it comes to pros and cons, since we're embedding in a cloud-based product, we're highly scalable. We are now doing some ML, but without having the need to gather our own training data, design our own architecture, train our own model, monitor and retrain. And this embedding, because it's fairly flexible can be done on either the raw text or the cleaned up version of the address that we produce during the second solution. But at the end of the day, it's a black box model. So we know that it was trained on a very generic corpus, so books, online content, etc. So that's not super applicable to our own data. That is very specific to a specific subset of text. We again depend on third-party data. So if Google wants to retire that model, then we got to find something equivalent or better. It's very costly without an enterprise contract. 10 days worth of compute could easily be a couple $1,000s. And then this model is really overkill in terms of the number of parameters. Even though the architecture is not public, based on the time it takes to make those predictions, people have estimated that this model has between 100 and 200 million parameters. So is there something a bit simpler and more tailored to this problem that we can design without having to go all in with these large language embeddings? So we'll start with model fine-tuning. So this is the sort of middle ground between full out-of-box model and fully customized architecture. The idea is that you take a model that has been trained, but you have access to all the internals of the model. So the architecture, you can change how, and then you can refine the training by forcing it to learn more, and not only learn more, but learn more about your specific problem. And so this is called transfer learning. So for this solution, I used open source models, so the old mini LM L6 that is available on Hugging Face. For those who are interested, this is the architecture. And then it has about 23 million parameters. So we're again going from a couple 100 million to roughly a 90% decrease in the architecture. And the reason I chose this model is because it was trained on over 1 billion sentences for semantic matching. So even though I couldn't find a model that was trained on exactly the problem that we're trying to solve, this is a step in the right direction, because this model was trained to look at two different sentences that were spelled differently and highlights the one that were sharing the same semantic meaning. Then what we have to do to perform the fine-tuning is come up with our own training data and then loss. So for the training data, I picked 5 million pairs that were basically outside of the 5 millions that we're looking at as our benchmark. And I augmented that data set with common typos, abbreviation, things like that. And then we trained that model on contrastive learning, so using the cosine similarity that we saw. So the model will be seeing two sentences at the same time, compute the cosine similarity between the two, and we'll have embedded in our data whether these are true matches or not. And the idea is that if the match is a 1 for positive, then we want the cosine similarity to go towards 1. And then if those two addresses were not a match, we want the model to design a cosine similarity that will converge to 0. We run that over a day worth of running on an M chip, so much lighter than the previous model, on batches of 32 pairs. And then we run the results on our holdout, which is the set of 5 million addresses across those 5 anonymized lines. We're getting an 83% match rate, so we're down about 6 points from the out-of-box model. It's surprising, but not too surprising, because we really reduced the size of the model, so the brain is only a tenth of the size of the out-of-box model. But we're able to go much faster since we're crunching far fewer numbers than the out-of-box model. We can perform around 300 embedding per second on a regular laptop, and then do the vector search in 3 hours on a regular laptop. So I think this approach has some potential, maybe for refinement, either increasing the size of the training data, revisiting potentially the fine-tuning, the parameters of the fine-tuning, but because I knew that wasn't going to be the end goal to stop at fine-tuning, I went with this sort of semi-optimal version that is showing me that even though we can compromise on the size of the model without compromising too much on the performance. As far as some of the common errors, the model is struggling for those addresses that were missing a postcode because we're increasing the pool of candidate by not being able to filter on a given postcode. The model is basically having a harder time at finding those matches. And then for the final one, we have the same issue of the incorrect semantic meaning of a street. So as far as pros and cons, we've got this time a lot more control because we can pick the architecture that we want, even though we're stuck with a tokenizer plus a model architecture. You have on a platform like Hugging Face access to thousands of models that have been trained. You can really spend time to find the candidates that you want to use, run either an immediate prediction without doing any fine-tuning, and sort of isolate which are the most promising candidates that should be considered for fine-tuning. And because now you have access to the model, you own that version of the model, you can go through continuous improvement, monitor the model, retrain as you get more data, and then make some tweaks. But now it's becoming a much more significant project because you're owning this ML pipeline, and so it becomes an ongoing project of monitoring the performance of the model, designing the deploy requirements. Because you are not using BigQuery built-in functionalities, you have to deploy your model somewhere, have GCP talk to this deployment so that you can run the query still efficiently on your millions of rows. In order to properly tweak a model, even though you're not crafting the architecture, it takes a lot of tuning, trials, and error because you're in charge of the training data, the loss function, and then the many parameters that go into the training setup. And then because it's a much more lightweight version of the out-of-box model, we are basically compromising a bit on the match rate. So going from there, there is one step left, that is building everything from scratch. So this approach will give us the maximum control and optimization, but it's also the most complex one because we've got to design everything. So we're going DIY all the way. The model that I've chosen is a lighter version of the one that we just saw that was taken from Hugging Face. And the idea here was for me to answer the question, can I beat a model that is bigger but trained on something less specific than the problem I'm trying to solve with a model that is lighter but trained on with a lot more purpose? So that means that because we're training this whole architecture, every parameter starts from a random state. There is no pre-baked knowledge in that architecture. We're throwing a lot more data in this model. So we're starting with 40 million pairs that are taken from outside of the validation that we're working with. And we're also augmenting the data with some synthetic variations. As far as the architecture, we're basically going from 23 million parameter to 5 million. So again, cutting by 75%. And then for the loss function, I experienced with two different phases. The first one was, let's have the model understand the semantic meaning of the addresses by looking at individual pairs and computing the cosine similarity. So basically the model will look at two addresses and try to get a score of 1 if it's a true match and a score of 0 if it's not. But then exploring what is available in terms of the losses you have access to, one of the interesting one is this multiple negative ranking loss, because it's designed for a model that will have to create a ranking and then pick the top 1, top 2 predictions. So that means that not only with this loss function, we're looking at creating a high similarity score between matches. We're also telling the model, hey, look at this one batch. This is the query. Now I'll rank everything in the right order, and I really want to see my true label at the top, otherwise you get a pretty big penalty. Because, again, we're training the entire architecture, we're running on 4 days worth of training, and then we'll perform the validation on the set that I've been covering throughout this talk. I want to talk a little bit about this custom loss function, because basically this process is very similar once it's all laid out, and the two that we've seen before. But I wanted to show something that has, in my opinion, a pretty big impact when designing your pipeline, which is doing some research, some reading on the large diversity of loss function that you can use. So using a classification model, you are not stuck with just cross entropy. You can find something that is a lot more curated for your application. And in this case, I'm using this MNOI. So the way it works is you start with a batch. In our case, we're starting with 4 addresses. They're purposefully very different, so it's kind of easy to see and to read. And those are true pairs, meaning that the query for pair 1 corresponds to the true ground truth for pair 1, and we do pair 2, pair 3, etc. The way that loss works is you'll start by embedding each side. So you'll start with 4 anchors that are your queries, and then 4 positive that are your match rates. So you get those 8 vectors. And then you're going to compare each query against the 4 candidates. And so creating this matrix basically of multiple scores for every given query. And then you can create a ranking. So in this case, let's see if I can get there. Yeah. So this query A1, we know it matches with the positive 1, so we want the highest score to be there. And we want the similarity between query 1 and pair positive 2, 3, and 4 to be really, really small, so that P1 ranks at the top, and then these have to be ranking really low. And then we do the same thing for the rest. So you want the scores on that diagonal to be as high as possible. Even though that loss function is really appealing, I think there's some very easy pitfall. The first one is if your batches are too easy, so if just like this one, if your addresses are very different, the model won't learn anything. Those are obviously so different that the model can easily pick that pair 1 matches 123 Main Street in Boston, and pair 2 is the one in Texas, etc. So you not only want to create those batches from a proper training data, but you want to make sure that you craft them so that you're making the hardest possible time or creating the hardest possible scenario for your model to really learn something interesting from that batch. So in that case, we had to create batches of 32 or so addresses that were very, very similar. So there's a lot of like filtering and sorting these couple million addresses. So you can get to a point where now each batch is really, really hard, and the model will learn something. Because otherwise, the model won't learn much, so when it's live in the wild, it won't create a good ranking. So that's why I use this as a second training path. So we started with contrastive loss, and then we did one more run of training with this specific loss function. And we get to 88%. So we're down basically 1 point from the out of the box and 2 points from the API, which is, I think it's pretty good considering that we're likely 50 times smaller than the out of the box model, and we're a fraction of the cost of the API. And so that means that inference will be much faster. We're going from 300 to 500 embedding per second by decreasing the size of the model. And then 2 hours for the vector search. We still require the same filtering throughout based on house number, postcode, and state to reduce the number of candidates so that the vector search is not this massive monster of computation. As far as some of the errors go, we're hitting the same issue of not having access to the postcode. And I purposefully left this untouched. But there are easy ways you could correct that. You could store a mapping of every city, and the value would be every postcode, and then backfill all these addresses. So that would make things a little faster here and a bit cleaner. The reason I left that untouched is because I wanted to see how raw can we keep the data and still get some decent results. So adding the data backfill for those missing components would be a natural next step for this project. As far as pros and cons, so we've got the most control, meaning that we are owning the full architecture. Here, we're also in charge of the tokenizer, so that means that the tokenizer was trained specifically on just addresses, and so we were not looking at full plain English text. It was just American addresses. Same thing, we chose the architecture to be the size that would allow us to run all those predictions within the time frame that we want. But it comes, at the cost of many iteration over the architecture, the model parameter. It's a lot more time spent, a lot more resources have to be involved, and then the training has to be carefully designed on likely cloud servers, so then you have access to GPU or TPU to train the model even faster. And just like the fine-tuning, now that project is your responsibility, so you have to be continuously monitoring the match rate, so you're looking for possible degradation, or whenever your vendor updates their data with new or retire US addresses, you want to retrain your model. So where does that basically leave us? What I want this conclusion to be about is to give an overview of all the solutions that we had access to, and why there isn't a right answer. If we all had to run this problem based on our constraint and the product we work with, we would all use one of the various flavors of those solutions. So we see that these solutions, they're, except the raw data, increasing the complexity leads to better performance. And also, unfortunately, increasing the money you throw at this problem, whether it's for more compute or a larger model, will also increase the performance. If we had to pick one, probably the out-of-the-box model would be a good candidate. But I think it would be too limiting, and also involve a ton of computation on a lot of that data, that 47% we see on the first row, that is basically free matches that you get by using just a simple join on two data sets. So the solution that I think I'll eventually use in production is a waterfall approach, where we start by doing the raw match. We get that 47% match rate for free. We don't need to do any embedding. We don't need to do any data cleaning. In some cases, that 47% will be higher as a starting point if the client we're working with has better data, and sometimes it might be worse. Like if it was that financial client, it would start at 0. Then we would get into the pretty fast and open source cleaning and parsing, and we get that extra 29% for free. And then you get into the more complicated solution that would require the embedding and then the vector search. So using likely the custom model to get us to the 88. And then if your budget allows it, and if you're still not sold on getting an 88% match rate, you can still now get the last 3% on a third-party API. And then you're left with the 10% on match at the end. So this hybrid approach, I think, is a good balance between the complexity. I mean, obviously now you're in charge of those regex, that custom model, so you add a little bit to your plate, but at the price of reducing significantly your cost, your compute cost, and then the number of calls you're making to that custom API, which is why I think it's probably an ideal scenario, especially when we see how much we're getting at each time. We're having fewer and fewer addresses being passed to the next step. And that's all I got for today. Thanks for your time.